We continue with practice questions, and the first question here. The diagram below shows the boiling point trend of group 14 hydride. First question, what is an instantaneous dipole? First, to understand the meaning of a dipole is a compound that has got a positive charge and a negative charge. For example, water. So water has got hydrogen, which is partially positive, and oxygen, which is partially negative. So it has got two different poles, so meaning dipole. Now an instantaneous dipole is a dipole that is caused by fluctuations or distortion in the arrangement of electrons. If you have got an atom where you've got electrons in the center of the nucleus like that, not really in the nucleus because electrons are not found in the nucleus, electrons are found in shells. Okay, you have got electrons in the shells. Now, if you distort these electrons, you change them the way they are. Maybe you take them, you concentrate them to one side. The way it is, this compound, it is not charged, but if you make the electrons concentrate on one side, this side where the electrons are going to become will be partially negative because the electrons are negatively charged. The other portion is going to be partially positive, forming a dipole. So such a dipole is called an instantaneous dipole. Therefore, an instantaneous dipole is simply a dipole that arises from temporal variation in electron density. So you've seen that electrons will be much denser this side as compared to that one. So that is instantaneous dipole. Now, use the concept of polarizability to explain the trend in the diagram. The question is, why is it that this compound has got a much higher boiling point in comparison to this, that, and that? Well, when you're talking about polarizability, this is simply the ease with which electrons are distorted. So if you have got an atom or a molecule or an ion, it has got electrons. How easy are you able to distort these electrons? How easy are you to make them concentrate on one side such that it becomes now polar? Okay, it becomes polar. So this side now becomes negative and then this side becomes positive. So polarizability, the ease with which electrons are distorted, increases with increase in molar mass. If you have got a substance with a higher molar mass, it means it has got more electrons, and the higher the number of electrons, the easier it is for you to distort them so that they concentrate on one side. And the easier it is to distort them, the stronger the bonds, or let me say the higher, let me say the more powerful the intermolecular forces it can form. Because if you can easily distort the number of the electrons arrangement, you concentrate them on one side, you are going to form a polar substance. It becomes much polar, and this is just temporal. It's just at an instant. So when this happens, when you form something like this where electrons are concentrated on one side, this substance now can be able to attract others to itself. And so if you have got a lot of electrons concentrated on one side, it can attract others and form greater bonds or intermolecular forces, that is between other different substances. That's the meaning of inter. So there will be greater intermolecular forces. So because of the higher intermolecular forces, and specifically what you're talking about when you're referring to intermolecular forces or in instantaneous dipole and polarizability, you're talking about London dispersion forces, which result from fluctuations in the arrangement of electrons. So we are going to form much stronger London dispersion forces, and London dispersion forces are formed in nonpolar molecules. You can say this is a nonpolar molecule, this should be also nonpolar, and that, and also the other one. So these are nonpolar molecules. So we are talking about London dispersion forces. That means if you have got a lot of electrons, you have got higher polarizability. The higher the polarizability, the greater the London dispersion forces. And so if you have got forces which are much stronger, that means they cannot, your compound you're talking about can attract other compounds much strongly. Because of that, it is very difficult to separate them. And that is why this compound which is on top has got a very high boiling point, because you can see the molar mass is very big in comparison to these others, and carbon has got the lowest molar mass. Even if you add the molar mass for hydrogen, it will still be lower than all these. That is why. Let's consider the next question. If the radiator of an automobile contains 12 liters of water, how much would the freezing point be lowered by the addition of 5 kg pre-stone, which is glycol, having that molecular formula, and that is the molar mass? How many kilograms of xenon, which is methyl alcohol, would be required to produce the same result? Molar freezing point depression constant is been given 1.86 degrees Celsius per molar. Assume the density of water is 1 gram per milliliter. Now, the first question is asking us, if the radiator of an automobile contains 12 liters of water, how much would the freezing point be lowered by the addition of 5 kg per stone? So I want to find the freezing point lowering, also called the freezing point depression. When you have got pure water, water we know it boils at 0 degrees. If you add anything to water, the boiling point is going to be reduced. So I want to see how much lower it is going to go. So change in freezing point is given by negative the freezing point depression constant multiplied by the molarity multiplied by also the Van Hoff constant. Van Hoff constant is 1 for any compound that doesn't dissociate or non-electrolyte. For example, organic compounds, carbohydrates, and sugars, others just like that, they don't dissociate. So the Van Hoff constant is always 0. But for substance which dissociate, depending on the number of ions which they can form, that gives you the Van Hoff constant. When sodium chloride dissociates from sodium ion and chlorine ions, so just add these, you have got 2 charges. The Van Hoff constant is going to be 2. If you're talking about aluminium 3 plus and chlorine, when they react they form aluminum chloride, Van Hoff constant is going to be 4 because you have got 4 charges there. Well, let's go on and calculate. Now the first thing is we don't know the molarity of pre-stone. We've just been given the mass and the molar mass of pre-stone, and it has been put in 5 liters of water. How do we get to calculate the molarity? We know that molarity is given by number of moles of solute, what you are dissolving, divided by the mass in kg of the solvent, what you are dissolving into. But same, we don't have the mass for water. All we have is what? The volume. And they've given us also the density for water. And how do we get to calculate the mass from density and volume? We know that mass is equal to density times volume. So let's go on and calculate. The density is 1 gram per milliliter, and the volume we've been given is 12 liters. We see this is in milliliters, this is in liters. These two are not able to cancel out, so we need to express them in the same unit. But let me just write that down here so that I get to have space. So I'm saying mass is going to be density multiplied by volume, and the density is 1 gram per milliliter times volume, which is 12 liters. To convert them to the same unit, what we are going to do is I'm going to multiply. Okay, we know that we have got a liter on top, so for me to convert a liter to milliliters, what I'm going to do is I'm going to take a liter down and then a milliliter on top. In 1 liter we have got 1,000 milliliters, so this milliliter and the milliliter cancels, the liter and the liter here also cancels out. Now I want the answer to be in kgs, so I'm also going to convert the grams to kg. And how do we do that? We know that, so I'm going to take a kg down. Okay, not down because we want a kg to be on top and we want a gram here to cancel, so I'm going to take a gram down. And we know that in 1 gram we have got 1,000 kgs. So this is going to give us, this value is going to cancel out with this value. Okay, so this will simply be 1 gram, and the gram here is going to cancel out with the gram. So our unit will simply remain in kg. So it will just be 1 times 12, and that is going to give us just 12 kg as the mass. Alright, so that is going to be the mass. Now we are going to go on and substitute our mass there, which is in kgs. But what's the number of moles? How do you determine the number of moles of solute? Number of moles is given by mass over molar mass. We are talking about 5 kgs. But we don't want to work with kgs, so we're going to multiply. We know that in 1 kg we have got 1000 grams. So this kg and the kg cancels. We have converted this value to grams and then divide by the molar mass of pre-stone, because this is pre-stone we are talking about. The molar mass is 62 grams per mole. So same, this gram which is here will cancel out with this gram. So if we punch on the calculator 5 multiplied by 1000 and then divided by 62, let me just punch that. 5 multiplied by 1000, that will be 5000 divided by 62, that will be about 80.645 moles. So you can now go on and put there 80.645 moles divided by the mass, which is in kgs, and the mass we found 12 kgs. So if we do the division, 80 divided 0.645 divided by 12, this is going to give us 6.72 mole per kg is what we call molar. It is small m, not capital M. Capital M is molarity. This is molarity. So there is a difference. Now let's go on and substitute our value. This is going to give us negative kf, that is 1.86 degrees Celsius per molar, and then the molarity, that is 6.72 molar. The Van't Hoff constant, this is an organic compound. The Van't Hoff constant is 1. It doesn't disassociate. So that will be negative 1.86 times 6.72, and that is going to give us negative 12.5 degrees Celsius. Okay, so this is how much the freezing point is going to be lowered. Now the next question: how many kilograms of xenon having this molar mass would be required to produce the same result? What result? Producing this same change which we have here. So we are saying change in freezing point is equal to negative kf mi. Now also we are getting xenon and putting it in water. Okay, we get xenon and dissolve it in water. So the change is simply the same, negative 12.5. That is the change that we want to see. But that is equal to, of course we are still dissolving it in water, and Kf for water remains the same, 1.86. There is a negative in front. And then multiplied by the molarity times Van't Hoff constant. This is also an organic compound. It is still 1. So we'll see that this will just give us negative 12.5 is equal to negative 1.86 m. So divide by negative 1.86 both sides. So the molarity is going to give us, if we divide both sides by negative 1.86, that is going to give us 6.72. And we know that molarity is in mole per kg, which is molar. Now the question is how many kilograms. So we just want the answer to be in kilograms. And how are we able to do that? Well, we are going to just get this term and convert it into mass. How can we convert into mass? Firstly, we know that number of moles is equal to molarity multiplied by the mass of the solvent. How is it? That is because molarity is equal to number of moles of solute over mass of solvent. So I've just rearranged the equation which I wrote earlier. So the number of moles, that is first what we want to get. So the molarity we've determined 6.72, and this is in mole per kg, and then multiplied by the mass of the solvent, and the mass should be in kgs. We already determined the mass of water as 12 kg. This we already calculated earlier. So the kg and the kg is going to go, and this is going to give us about 80.645 moles. So this is the number of moles of solute which you've added. Now convert these moles into mass, and we know that mass is number of moles times molar mass. So this is going to be 80.645 moles times the molar mass, which is already given there, 32 grams per mole. The mole and the mole cancels out, so that is going to give us about 2461.538. It is in grams, but we want the kilograms, so we'll convert this to kilograms. We want a kilogram on top. We know that in 1 kilogram we have got 1,000 grams, so the gram cancels with the gram. 1,000 into this number, that will give us about 2.46 kg. So this is going to be the value then. The next question here: a solution containing 250 milliliters of water and 48 grams sucrose was prepared at 300 Kelvin. Pure water was separated from the solution by means of a semi-permeable membrane. What must, so that should be must be the applied, what pressure must be applied above the solution in order to prevent osmosis? What pressure must be applied above the solution to prevent osmosis? Now, what really are we talking about? Well, this question is just talking about osmotic pressure. So osmotic pressure is simply the minimum pressure that you have to apply to a substance for you to prevent osmosis. Osmotic pressure is the minimum amount of pressure that you have to apply to the solution side to prevent osmosis, and it is given by molarity multiplied by the universal gas constant multiplied by the temperature and then Van Hoff constant. So this is the osmotic pressure. That is the pressure that we need to apply just to prevent osmosis from happening, or the movement of substance from happening. Now, what is the molarity? Molarity, we know, is the number of moles over volume. That is number of moles of solute divided by the volume of solvent, that is where you've dissolved into, then multiplied by R, multiplied by temperature, multiplied by the Van Hoff constant. Now the number of moles: a solution containing 250 milliliters of water and 48 grams sucrose. Okay, we've been given the grams of sucrose and the molar mass. How do we determine the number of moles? Number of moles is given by mass over molar mass. So where there is number of moles, I'm going to put mass over molar mass, so that will become mass over molar mass, and then we have got also volume there in the denominator. Okay, and then RTI. So we'll go on and substitute the values. The mass given is 48 grams, and then I'll just multiply first with the universal gas constant. The universal gas constant which we are using is 0.08206. It's just to look at the units that you are dealing with. So this one is in liters atmosphere, okay, per mole Kelvin. So I'm going to put the unit down there because it means pay. And then on top we also have the temperature. Now the temperature should be in Kelvin because we're talking about Kelvin here on the unit for the universal gas constant. Where is the temperature? 300 Kelvin, that is there. The other thing that you have not put is the Van Hoff constant. Talking of sucrose, sucrose is a sugar and the Van Hoff constant is a 1 because it is also an organic compound. And then in the denominator we have got the first molarity, which is given as 342.34 grams per mole. Okay, because I'm talking of grams per mole, this is already grams, we are saying per mole. This mole is going again down, so it is down. This number is already in the denominator and the mole goes in the denominator again, so that would be more like it goes on top, but I can write it there times now the volume. The volume of the water is 250 milliliters, Now we don't have any milliliters here, we only have liters, so we need to convert that value to liters, and that is just by dividing by 1,000. So that would be 0.25 milli, I mean it becomes now just liters. So we can now see the units are going to be cancelling out. Liter cancels with liter, more cancels with more, Kelvin cancels with Kelvin there. What of this gram, it cancels with the gram there. So the only unit that is going to remain is atmosphere, and that is the osmotic pressure, and that is going to be equal to about 13.8069052 if we punch on the calculator, which you can just write as 13.8 atm atmospheres. Alright, now the next question here: estimate the osmotic pressure in atm of 10 grams per liter of a solution of a non-electrolytic macromolecule of molar mass 1.00. That was supposed to be times 10. Okay, times 10 to the power 4. Let me just complete this one. Times 10 to the power 4. Now how do we get to find the osmotic pressure? Just as we've seen in the previous question, osmotic pressure is given by molarity multiplied by the universal gas constant times T times I, which is the Van Hoff constant. Now molarity is the number of moles over volume. Now estimate the osmotic pressure in atm of 10 gram per liter of solution. We've already been given the solution, so that means this given value here is already the concentration. So the concentration has already been given. It's just that it is not in terms of molarity. It has been given as density, but there is a relationship between molarity and density. So what we'll just do is we're going to get this value and put it here. We're talking of 10 grams per liter. Okay, and we are going to multiply this by, firstly we are talking about a macromolecule of molar mass. They've given us the molar mass there. So if we simply multiply the molar mass and the density, what do we get? Let's see what happens if we multiply by the molar mass. Now I'm not going to really multiply by the molar mass, but by the reciprocal of the molar mass. The thing is, I want to see these units cancelling out because I need to see only atm at the end. So this value has been given as 1.00 times 10 to the power 4 grams per mole. What does this tell us? That means in 1 mole of this compound we have got 1.00 times 10 to the power 4 grams. So that is the same. Grams per mole means 1 mole in contains that amount of grams. The reason as to why I've done this is because the gram here and the gram is going to cancel, and so you can see now it is mole per liter. So if you just multiply the density and also the molar mass, you get the concentration, which is molar, and we are going to multiply this by the universal gas constant, and that is 0.08206, which is in liter atmosphere per mole Kelvin. And we're also going to multiply this value by the temperature of the solution, and that has been given as 25 degrees. So convert that to Kelvin. So that will be 25. Just add 273 to that value. That will be now in Kelvin. So you can see a Kelvin cancels with a Kelvin there. A mole here also cancels with a mole there. So even a liter, which is here, is going to cancel with a liter there. The only unit is going to be atmosphere. And so this is going to give us about 0.024466189, which we can just approximate as 0.02 if we round off to one significant figure, atm. Alright, next question here: calculate the concentration of carbon dioxide gas dissolved in Coca-Cola soft drink if the manufacturer uses 2.4 atmosphere to carbonate it. The Henry's constant for carbon dioxide at 25 degrees Celsius is 3.36. This is also times 10. Okay, that is 3.36 times 10 to the power negative 2 mole per liter atmosphere. Now, how do we get to find this? Well, when we're talking about the Henry's constant, the obvious what should come in our minds is Henry's law. Whenever we're talking about dissolving something, and we are relating concentration with pressure. That is about the Henry's law, and the Henry's law tells us that the concentration is directly proportional. The concentration of gas dissolved in a solution is directly proportional to the pressure of the gas above the solution. So here we've been already given the Henry's law, which is 3.36 multiplied by 10 to the power negative 2 mole per liter atmosphere, and we are multiplying this by the pressure. The pressure has been given as 2.4 atmosphere above the solution. So you see atmosphere and atmosphere cancels out, and so this is going to give us a value of 0.08064, which I can also write to in standard form as approximately 8 point. I remove a 1 from this 6 to put there. That would be 8.1. That will be times 10 to the power negative 2 mole per liter, and mole per liter, that is molarity. All right. The next question: when 30 grams of a non-volatile solute having empirical formula of CH2O is dissolved in 800 grams of water, the solution excuse me, the solution freezes at negative 1.16 degrees Celsius. Now, the question is, what is the molecular formula of the solute? Well, what is the molecular formula of the solute? Forgive me for that, for the typing error on this one. Talking of the molecular formulae. But what information do we have here for us to calculate the molecular formula? We've been told that when 30 grams of a non-volatile solute having the empirical formula CH2OH is dissolved in 800 grams of water, the solution freezes at negative 1.16 degrees Celsius. That means we've lowered the freezing point, because water freezes at 0 degrees, but now it is freezing at negative 1.16. So we're talking about freezing point depression, and change in freezing point is given by negative molar freezing point constant times the molarity times the Van Hoff constant. So we're talking of the change. The actual freezing point for water is 0, but it now freezes at that value, which is negative 1.16. Okay, the solution freezes at that temperature, and because this is a change, my writing was wrong. A change is always final minus initial. So the final freezing point here is negative 1.16, but the initial freezing point for water freezes at 0. So that is supposed to be the right way. That is going to be negative Kf, that is 1.86, and then multiply by the molarity. Do we know the molarity here? No, we don't know the molarity. What is the Van Hoff constant? They've told us the non-volatile, and just by looking at the empirical formula, this is an organic compound. It doesn't disassociate. The Van Hoff constant is the 1. So to remain with just molar, we're going to divide by negative 1.86. Even this side divided by negative 1.86. So the molarity is going to become, if we divide the two values, that is going to give it up about 0.623655914. Molarity is in mole per kg. Okay, that is it. Now that we've determined the molarity, we can get the number of moles from here. We know that molarity is given by the number of moles of solute divided by the mass of solvent. The molarity we found 0.623655914, and this is going to be equal to number of moles of solute. We don't know the number of moles of solute which we dissolved, but the mass of solvent we've been given when 30 grams of this compound dissolves in 800 grams of water. So we divide by 800 grams. Okay. Well, we are dividing by 800 grams, but the molarity, we've seen that it is in kg, so we need to convert 800 grams of water to kgs. So just divide the value by 1000. That is going to be 0.8 kg. Okay, so that is the right unit in which it should be. So just multiply these two. That will give us the number of moles of solute, and that is going to be equal to, if we do the multiplication, that will give us 0.498924731 moles. Now these are the number of moles which were dissolved in solution. Okay, now another thing that we need to determine is the molar mass of this compound. How do we get to find the molar mass? We know that number of moles is mass over molar mass. So from here we can determine that molar mass is equal to the mass actually, divided by the number of moles. And the mass of which was dissolved for this compound is 30 grams. The number of moles which we have calculated which was dissolved is 0.4989247 moles. So if we divide these two values, we are going to get 60.1293. On top we have got grams, down we have got moles. So this is the molar mass of the compound. Now we've been given the empirical formula. So let's calculate the empirical formula mass. And how do we get to calculate the empirical formula mass? We just get the empirical formula itself and look at the compounds which we have, the elements which we have. So that is CH2O. We have got oxygen having a molar mass of, that is 16. Hydrogen having, we have got two of them having a molar mass of 1. We have got carbon which is having a molar mass of 35. So what value are we going to get? All we have there is 16 plus 2 plus 35, and that is about 53. Now the values which I've used here are really not the actual values but just approximates. So instead of using 16 for oxygen, let me use 15.9994, and then hydrogen 2, let me use 1.008, and then for carbon let me use 34.54. Okay, so this will give us 15.999994, and then plus 2 multiplied by 1.008, and then plus we have got 34.54. So that will give us about 52. Okay, let's see the molar mass that I calculated. Perhaps I'm using also a wrong value. So this is supposed to give us the molar mass of CH2O. Okay, carbon, I'm using a wrong value. Sorry for that, because the value that I'm using here is not the molar mass for carbon. The molar mass for carbon is just 12, not 35. So what I was using is for chlorine, 12.01. Okay, that is the value that we're supposed to use. So we're saying 12.01. If we sum these up, that is going to give us 30.0254. It is in grams per mole, like that. And the main instance of me finding the empirical formula mass is I know I need to find N, which is the molecular mass divided by the empirical formula mass. And here the molecular mass is about 60.1293 divided by the empirical formula mass, which is 30.0254. Empirical formula mass is simply the value which we get from the empirical formula if we get the molecular mass of the empirical formula, and that is going to give us a value which is approximately 2, because we need to use a whole number. Now we can determine the molecular formula. And how do we get a molecular formula? Molecular formula is simply equal to empirical formula and then N. The empirical formula here we've been given is CH2O. And then N we've determined 2. So this will give us a molecular formula which is C2H2 times 2, that will be 4, and then O2, that becomes the value. Next question here. Identify and describe the intermolecular forces between solution components in an aqueous sodium chloride solution. Aqueous sodium chloride solution. First thing, we want to identify the intermolecular forces which are in this compound. After identifying them, we want to describe them. Okay. Now, let's first look at aqueous sodium chloride. Aqueous sodium chloride contains what ions? There are sodium ions, there are chlorine ions. Because it is aqueous, that means it's in water. And water can actually dissociate to hydroxide, but mostly that doesn't happen really at room temperature. But we have got water which is polar. Okay, these are the substances which we have. So in aqueous sodium chloride, the first kind of intermolecular forces which we have, these are ion to ion intermolecular forces. So we are saying ion to ion because we have got ions in this aqueous sodium chloride solution. For example, we have got sodium ions. Let's say if the water dissociates, then we are going to have also hydroxide ions. So these are going to be interacting, the negative and the positive charges are going to be interacting. So this will be an ion to ion interaction. And the other kind of intermolecular forces which we have is ion to dipole. Or let's say if it is not a water which produced hydroxide, we are also having chlorine ions, because sodium chloride has got sodium ions and chlorine ions, and this can dissociate. Chlorine from another compound can come and interact with the sodium from the other compound. Now ion to dipole, we have got ions such as sodium ion. This can interact with the dipolar water. Okay, so what is going to happen is the negative portion of water, that is the oxygen, is going to surround the sodium like that. And also the chlorine, which is negative charge, will be surrounded by the water, but water is going to align itself in such a way that the positive part for water, that has the hydrogens, will be interacting with the chlorine in such a manner. Okay, so these are the intermolecular forces which we have in sodium chloride. Besides that, we also have London dispersion forces, LDF, or Van der Waals forces. Now these forces are found basically in all compounds, and they are due to distortion of electron cloud. Anything that has got electrons is going to contain London dispersion forces. Whenever electrons are distorted, a compound begins to interact. Alright, so these are the types of forces which are found in a solution of aqueous solution of aqueous solution of sodium chloride. Alright, now the second question we have, the compounds, we have carbon chloride and also carbon iodide, have similar intermolecular forces. One of the compounds is a liquid and the other solid under standard conditions. Now the first question is, what type of intermolecular forces are present? Well, if we can draw Lewis structures for these compounds, you have got a carbon on the middle and then surrounded by chlorines like that. Same way, you've got carbon on the middle surrounded by iodine like that. So these are necessarily non-polar compounds. And for non-polar compounds, because the net dipole is going to be 0. If the dipole goes, let's say, towards iodine or towards carbon in that direction, even this one it goes like that, even this it goes like that, they are going to all cancel out because they are all going in the same direction. So these compounds, both of them are non-polar, and for non-polar compounds, the only intermolecular forces which exist within them is the London dispersion forces, which are due to the fluctuations of electron cloud or distortion of electron density. Now the second question we have, identify the liquid and the solid compound. Justify your answer. How do we identify which one is going to be a solid and which one is going to be a liquid? So that has to do with the concept of polarizability. Okay. So polarizability is simply the ease with which electron cloud can be distorted. And the bigger the compound, in other words, the higher the molecular mass, the more the number of electrons, and the more the number of electrons, the higher the polarizability. And if a compound can be easily distorted, the electron cloud can easily be distorted, that means it can form greater London dispersion forces. And so we just look at which one has got a higher molar mass. So in comparison, carbon chloride and carbon iodide. Okay. So the one which has got the molar mass which is higher is carbon iodide. So because of that, okay, let me just check first the value of the, of course carbon is the same. Now we're comparing chlorine and iodine, which one has got a higher molar mass. Alright. So from here we are seeing that carbon has got a higher molar mass. So since the molar mass of this compound, okay, no, carbon doesn't, carbon and carbon, they have got the same molar mass, sorry for that. And chlorine here, in comparison to this, iodine has got a higher molar mass in comparison to chlorine, if we check from the periodic table. So because we have got 4 of iodine and then we've got 4 of chlorine, well, we can remove just carbon. We can remove carbon, but in comparison, just chlorine and iodine, iodine has got a greater molar mass. So because this compound has got a higher molar mass, it has got a higher polarizability. That means the electron cloud can be easily distorted. And what is the result of that? Since it has got a higher molar mass, it has got a higher polarizability, it means it forms much stronger London dispersion forces. And if it forms much stronger London dispersion forces, that means it is very difficult for you to separate it. Okay. In other words, the bonds are highly attracted to each other. The molecules or the atoms are highly attracted to each other in this compound because of the higher polarizability. And we know that solids particles are more held closer together than in liquids. So therefore, this compound is a solid and this one is a liquid. Okay. So that is how we can explain that. Now, question 9. A solution was made by dissolving 3.75 grams of pure hydrocarbon in 95 grams of acetone. The boiling point of pure acetone is 55.95 degrees Celsius, and that of the solution is 56.50 degrees Celsius. Now the question is, if the molar boiling point constant of acetone is 1.7 degrees Celsius kg per mole, what is the molecular mass of the hydrocarbon? Okay, so really what is the question talking about? We've been told that if we have got a solution which is made up by dissolving 3.75 grams pure hydrocarbon in acetone. So first we have got acetone. Now in acetone we dissolve this hydrocarbon and the boiling point of pure acetone is 55.9 degrees. After we dissolve this compound, we've seen that the boiling point has done what? It has increased. So this is boiling point elevation. This is a colligative property, boiling point elevation. That is the first thing that we need to get to identify. Now from there, how can we work out this question? Well, we know that change in boiling point is given by Kb, which is the boiling point elevation constant, multiplied by the molarity multiplied by the Van 't Hoff constant. Okay, that is what we have. Now here the change in boiling point, the final boiling point that you've seen is 56.50. The initial one we've seen is 55.95, and this should be equal to the Kb, which is 1.71 multiplied by the molarity. So in this case, let's say we don't know the molarity M, and then multiply by the Van 't Hoff constant. Now this is an hydrocarbon. Van 't Hoff constant is a 1. So our value here is to find the value for M. And to do that, we just have to punch this on the calculator. Let me just go on and punch the values which you have on a calculator. So that is 56.50 minus 55.95. Okay. And then that value that we are going to get, we are going to divide it by 1.71. Okay, let's determine that. 56.5 subtract 55.95 and then divided by 1.71. So that is giving us molarity, which is equal to 0.321637.426. We know that molarity is in moles of solute per kg of solution. Now what do we want to calculate? The molecular mass of the hydrocarbon. Well, the first thing is we need to understand the number of moles of hydrocarbon which we had to dissolve. And from this formula, we know that molarity is equal to number of moles divided by the mass in kg. So the number of moles which is dissolved is equal to molarity multiplied by the mass in kg. Now this mass is the mass of the solvent where we dissolved into. So this is going to be equal to the molarity we've already determined, 0.321637.426. This is in mole per kg. And we're going to multiply this by the mass in kgs. So where did we dissolve into? So this mass has been dissolved in 95 grams of acetone. So I've dissolved it in 95 grams of acetone, but these two won't be able to cancel. So we need to convert the 95 grams to kgs. We know that in 1 kg we have got 1,000 grams. So the kg will cancel with the kg and the gram will cancel with the gram here. So we'll just get the value which we have, 0.3216 multiplied by 95 and then divide by 1,000. That will give us 0.030555 moles. That will be it. Now that we have got the number of moles which were dissolved, how do we determine the molar mass or the molecular mass? Well, we know that number of moles is mass divided by the molecular mass. And this gives us that molecular mass is simply mass divided by the number of moles. And the mass which was dissolved, 3.7 grams, dissolving 3.7 grams of pure hydrocarbon. So 3.75 grams, and then divide that by the number of moles, is 0.030555 moles. So this is going to give us 3.75 divided by the value which we have. That is going to be 122.7272727, which we can just give as 122.7. That will be in grams per mole. Alright, now Let's consider the last question which we have. Okay, before the last one, we have got first question 9. Now, what type of intermolecular forces are present in H2S? What type of intermolecular forces are present in H2F? Now, how do we get the intermolecular forces which are present in this compound? First, we need to understand its Lewis structure. The Lewis structure for this compound is like that. Okay, in that manner. This one has got two lone pairs like that. Okay. So because of this, electrons are more drawn closer to the sulfur. So it has got a net dipole towards the sulfur like that. So in other words, this is a polar compound. So firstly, what type of intermolecular forces are present in the compound? Firstly, due to the net dipole, then this compound can have dipole, okay, dipole to dipole interactions. Now the dipole to dipole interactions, that can be if you have H2S and then another H2S. This can attract each other in such a way that this is going to have a partial positive charge, this is going to have a partial negative charge because it is attracting electrons, which itself is more electronegative. Because of this, another compound which is the same, when it comes, the sulfur which is negative will be such like in this manner, and then the hydrogen which is positive will be in that direction. So these are going to attract each other. So that will be the intermolecular force dipole to dipole, to be the interaction between one dipole and another dipole. Okay. What of another intermolecular force? Well, other intermolecular forces that this compound can undergo, for example, when you mix it with, let's say, an ion, it can undergo ion to dipole because it's dipolar itself. So it can undergo ion to dipole, and then because it contains hydrogen within itself, if you react it with another substance, if you put it in a substance such as water which contains oxygen, whenever hydrogen forms a bond with either oxygen, nitrogen or fluorine, that forms a special kind of dipole to dipole interaction, which is hydrogen bond. So that is due to the hydrogen which is present in this compound. And also another kind of force, another kind of interaction what this compound can undergo or which can go through is a London dispersion force, which is also referred to as the Van der Waals force. Now a Van der Waals force is just found in any compound, and that is just due to the distortion of electron cloud. When the electrons are disturbed, the electrons are going to concentrate on one side, and because of that, they are going to make one side to be partially positive and one side to be partially negative. So these are the types of intermolecular forces which can find in such a compound. Now the last question here. Some water is placed in a sealed glass container connected to a vacuum pump tuned on, reducing the pressure inside. The water appears to boil and then freeze. Now draw the phase diagram of water to explain these changes. Well, the phase diagram for water, let's make it like that. So we have temperature on the x-axis and then we have got pressure on the y-axis. So for water, it will be starts like that. It goes in that direction, one line. Okay, let me draw it something like this. And then one line goes more like in that direction, the other one goes in that direction. That is how the phase diagram for water looks like, where you have got here as a solid, here as a liquid, and here as a gas. And for water, the standard pressure is on top of the triple point. The triple point is this point where everything exists in the same state. Water exists in all the three states of matter. At the end here you have got what is called the critical point, where on the critical point this region is a region where you cannot differentiate between a solid and a liquid. You have got what is called a supercritical fluid, where we've got both pure liquid and pure gas. It is a mixture of liquid and gas. You cannot differentiate whether it's a liquid or a gas. So that is it, and that will be all for this video. Thank you so much for watching. Stay blessed.